Now moving on to the word counting section. So first of all, we were able to take our Batman Begins movie plot and we were able to divide it into individual words, as you can see. Now what's the next thing that you can do? The easiest thing that you can do is actually count how many times every word occurs in this movie plot. So in this list, count how many times each word occurs. So we are giving this word list and we are initializing a counter and we are converting that into a dictionary. Let's just run this and it will be very evident. So as you can see, the came 31 times, a came 26 times, and came 26 times, etc. in this. And once we converted into dictionary, this is how the count looks like. But at the end of the day, you can see that this is in the decreasing order of frequency at the top. And you know that the came 31 times, a came 26, and similarly Bruce came 14 times. As you can see, if you just take the highest counter of words, usually these are the stop words, and we got Bruce, which is an important keyword for this movie, but the highest term frequency is of stop words. And how do you differentiate these words from this? Is because these words have high frequency in every other movie plot as well, if no matter which movie plot that you take. So the term frequency of these words is high in all other movie plots. But whereas if you take the word Bruce, its term frequency is high in only few movie plots. So if you take inverse document frequency, that is how many times a given word occurs across all the movie plots. Now if you multiply term frequency with inverse document frequency, that's when you will be able to get low scores for these ones, and you will be able to eliminate these things and keep only the important words. But nevertheless, what we have done here is simple. We have just collected how many times a given keyword occurs in this movie plot. And what's the next thing that we can do? So let's just print the most common words, and as you can see, we printed the most common 4 words, and they are called as stop words because they occur in high frequency, and the thing is that they occur in every other movie plot, so they don't carry much information. Now a lot of libraries like NLTK and Spacey, etc., they already collect popular stop words in every language. For example, in English, I have taken this from NLTK. So NLTK has already collected all these as stop words. This is a stop word list, and what we are going to do is that from the words that we collected here, we are just going to remove stop words. So we call this clean words list, and again we are splitting it, and what we are doing is we are iterating through every word. So we are iterating through every word in here, and if it's not in this stop words list, then only we are appending it to clean word list. So let's run this. As you can see, a lot of stop words are removed, and now you have Gotham City, Young, Bruce, all important keywords. So all the stop words are removed. So if you have new collection of documents, how do you calculate stop words? The simple thing is that, so you combine all the text, that is you create the complete corpus, and from all the text, again you split the text into tokens, however we did. Then from that you just calculate the highest frequency words, and the highest frequency words are basically the stop words for any new corpus, and you need to see where the difference is, where that split is happening from high frequency words that are mostly used to rare words. Then at that point you can split, and everything before that, the high frequency words, could be the stop words. So what that simply means is that either you can create your own stop word list from your own corpus, or you can use stop word list that is pre-calculated by other libraries like NLTK, Spacy, etc. Now the biggest question you might have in your mind is it always good to remove stop words? The answer is no. So let's take this example. I am flying from Delhi to San Francisco. If you remove all the stop words, then it comes out to be flying Delhi San Francisco. If you have second sentence, that is I am flying to Delhi from San Francisco, and remove, you'll get the same sentence. But here you're flying in the opposite direction completely, and that is not at all captured. So the thing to remember is that it's good to remove stop words only if you're dealing on a higher level task. That could be, similarity or something like that. But if you're dealing with a low level task, for example, depending on whether you have a not before a word, the sentiment of that sentence could change completely. So it is very important to even keep stop words. And when you go to higher level algorithms like transformers and other things, what happens is that automatically stop words etc. are just kept as it is, and those algorithms have advanced methods to take stop words as well and do predictions on them. So the short answer is that only if you're dealing on a very high level task like similarity and other things, it's good to remove stop words. But otherwise, if you're dealing with a granular task, it's important to keep stop words as it is, because the sentence information could be lost. And the other thing that we encounter quite a lot of times is if you have a word like developing, you can actually do lemmatization or stemming to convert this word to its root form develop. So just to revise again, stemming converts it into its root form, but that root form need not even be dictionary word, whereas lemmatization converts this into a root form where always that word is a dictionary word. So for example, what lemmatization does is two things. It converts the word into its root form. What that means is if you have something like developing, it could be converted into develop. Attending could be converted into attend. And the other thing is if you have plural forms like bats, it could be converted into singular form bat. So all the variations are converted to its root form, and all the plural forms are converted into its singular form as well. So if you are dealing only on a high level, it doesn't matter whether you have developing, develop, developed. All these things could be converted into just develop if you apply lemmatization. And what happens is that then the number of features or columns that you are dealing with will reduce, as well as you can improve the accuracy, because you will not have 3 different entries for different varying forms of developing. Similarly, you will not have 2 different entries for bats and bat. You will have just 1 entry for it. So during processing, you can also apply lemmatization if you want. And again, similar problems exist. For example, if you have a statement like USA is a developed country, and you have another statement like USA is a developing country, the context and the information changes quite a lot. Both of them are 2 different sentences that convey different meanings. And depending on your use case, if you are dealing on a high level task, maybe it's good to remove stop words, and it's good to apply all these things like lemmatization or stemming etc. It's perfect. But when you're dealing with granular task, maybe converting developed to develop or developing to develop changes the meaning completely. So like I mentioned, advanced algorithms split this word like developing into develop plus ing, 2 different tokens. That's one thing to remember. And the other thing that you might get into mind is, so if you have something like bat, how do you know whether it is a cricket bat or if it's a flying mammal bat? Both are 2 different things, right? That's also one of the shortcoming with TF-IDF. So if you have a word like mouse, it could mean a computer mouse or it could mean the rat. Now the problem is that TF-IDF doesn't differentiate between them and just has one entry, that is one feature or one column. That is also the shortcoming with TF-IDF. And again, some of the advanced algorithms that we'll see in the future, perhaps sentence transformers, etc., where depending on the context where mouse comes, there will be a different embedding or vector for that. Now let's continue ahead and run the cell. And what's happening here is basically we are getting the counter after we are cleaning the stop words. So once you remove the stop words, all the popular ones like the, a, and, to are gone. Only we kept Bruce, Batman, Ross. Ross is basically Ra's al Ghul if you know the movie Batman Begins. And what's the next thing that you can do after removing stop words and getting the count? You can basically normalize the count depending on the total number of words in this movie plot. So let's run this. And as you can see, we have total 738 words in this movie plot. And simply what we are doing here is we are iterating through all the clean word counts, that is after removing stop words. And what we are doing is dividing 14 by 738. So whatever values that we have, we are going to normalize every value by dividing it by 738. That's what is happening. Get the value and divide by the total count that you calculated. And as you can see, for Batman Begins movie plot, we got this. And how did we get this? First, we calculated each word and its frequency, that is the count of that word in that movie plot. And once we got that count, we removed all the stop words. Then for the remaining words, we divided the count by the total number of words in that movie plot. So what the value that you see here is normalized frequency of the word Gotham in the movie Batman Begins. And what is this essentially? This is nothing but its term frequency. As we have learnt, simply the normalized frequency of the word within a given document, here within the movie plot, how frequent Gotham is, the normalized frequency, that is 0.008, that's called as term frequency. And the term frequency of city in the Batman's Begin plot is this. Now what's happening here is that we split our Batman Begins movie plot by individual words, but if you just take 2 words or 3 words, etc., you can do the same. You can get the term frequency for a bigram, you can get the term frequency for trigram, etc. Let's just understand how do bigrams and trigrams look like. We are going to use the NLTK library. It's called as Natural Language Processing Toolkit. And we are going to take this sentence, Elon Musk sentence, as you can see here. All I'm doing here is first I'm word tokenizing it from nltk.tokenize, and I'm using the ngrams function from NLTK itself. Nothing too complex, just take this sentence and I'm tokenizing the sentence here, and I'm printing the tokenized words here, and I'm calculating bigrams and trigrams. Let's run this. As you can see, this is the tokenized version of the sentence, and if I just take bigrams, this is how it looks like. Elon Musk, in recent months. And if you just take trigrams, this is how it looks. And like I mentioned, basically you can get the frequency of bigrams, trigrams, and divide by the total number of bigrams, etc. And similarly, and just like how you calculated term frequency of individual words in this document, you can calculate the term frequency of bigrams and trigrams as well. Now we are not using that here for simplicity, but just remember that you can go from unigrams to bigrams, trigrams, and 4-gram word as well. That's what you need to remember. Now let's keep everything that we learned in a function. So this is nothing too complex. All I'm doing is, if you pass any movie plot, we get normalized counts, that is the term frequency of each word here. That's all it is doing. So this whole function does the same thing. So you will get your term frequency, which is, you can pass in Batman Begins movie plot and just print the term frequency. So just you can pass in any text here and you will get the term frequency of each word corresponding to the text. So again, remember that term frequency just indicates how popular a word is within the document or plot. Now let's move ahead, and what we are going to do here is just print the data frame, and we have these 3400 movie plots, and what we are going to do is basically calculate term frequency dictionary for every movie plot. That's what we are going to do. So we have already created the function. All we are going to do is call this lambda that applies on every row, and in every row it applies the function get term frequency on this column, plot column, and it is going to append a new column called as TF with that plot column. Let's just see it. So nothing too complex. As you can see, for each word we got the normalized frequency, that is essentially the term frequency of that word in this plot, and we got term frequency of every word in the given plot. Let's run this, and you can see there are almost 3409 documents, that is movie plots. Let's just run this and see how it looks. So we are just printing 3 rows, and as you can see, what we just did was to collect all the words in a given movie plot and extract its corresponding each word's term frequency. And now one thing that we need to remember is that we do have some duplicates in the dataset. We have not seen it so far, but based on the Wikipedia link, that is the second column that we have, we are going to filter them. Let's just run this. So if you just run this, you will see that actually 3409 out of them there are few duplicates, and after filtering duplicates you just have 3379 movie plots. Still it's good number to work with, but just we are removing duplicates here.